Alamogordo, New Mexico, July 16, 1945. The dawn of the atomic age. The detonation of the first atomic bomb in history. From this beginning came the weapons that devastated the Japanese cities of Hiroshima and Nagasaki. From this beginning has come the vast atomic weapons program of the United States. No man can know every complex detail of the program today. But to work intelligently with atomic weapons, at least, the basic knowledge of the overall operation and what has been accomplished is essential.
The development, use, and control of atomic energy shall be directed so as to make the maximum contribution to the general welfare, subject at all times to the paramount objective of making the maximum contribution to the common defense and security. And the development, use, and control of atomic energy shall be directed so as to promote world peace, improve the general welfare, increase the standard of living, and strengthen free competition in private enterprise. Thus reads the Declaration of Policy of Public Law 703, more commonly known as the Atomic Energy Act of 1954.
Originally created by the Atomic Energy Act of 1946, the Atomic Energy Commission, in the space of a few years, has grown into a many-faceted organization for atomic energy. Established as a civilian agency directly under the President of the United States, the AEC was formulated to control the production, ownership, and use of all fissionable material and provide for research and development in the field of atomic energy. The AEC has continued and expanded the work started in 1942 by the Manhattan Engineer District. By taking over such wartime atomic energy facilities as Oak Ridge, Tennessee, where the scarce uranium isotope U-235 is separated from refined natural uranium by the gaseous diffusion process. The Hanford, Washington Active Material Production Plant, where uranium-238, the most abundant isotope in natural uranium, is converted into a completely new fissionable element known as plutonium-239. The Los Alamos Scientific Laboratory in New Mexico, where the know-how to use this active material is developed and where our wartime weapons were fabricated, and many other lesser-known but still vitally important facilities. Practically all of the production and research work at the Atomic Energy Commission is performed by industrial and commercial operating contractors and private and public institutions under contract to the Commission. Under the direction and overall supervision of the General Manager, the policies and programs formulated by the AEC's 5 commissioners are implemented by the Commission's various divisions. The Division of Raw Materials develops and directs programs concerned with the discovery and exploitation of sources of fissionable material both within and outside the continental limits of the United States. The Division of Research develops and supervises programs of research in or involving the physical sciences, including new equipment, new methods of instrumentation, and also in the dissemination of technical information. The Division of Production develops and directs the production of active material and manages related AEC installations and community activities. The Division of Biology and Medicine develops and supervises programs related to biology, medicine, biophysics, and is active in the program of making radioactive material available to medical science. The Division of Reactor Development develops and directs the use of atomic energy as the source of power, including the development of related equipment. Very important from the military standpoint is the Division of Military Application. To understand more fully the function of the Division of Military Application, it is essential to know something about the relationship between our atomic weapons program and the atomic energy program as a whole. As set forth in the Atomic Energy Act of 1954, our atomic program is directly under the President, with both the Atomic Energy Commission and the Department of Defense being responsible to him. Congress, through a joint committee on atomic energy consisting of 9 senators and 9 representatives, is kept informed of all activities of the AEC. Resolutions, bills, and all matters in Congress relating to the AEC or the development, use, or control of atomic energy are referred to this joint committee. A general advisory committee made up of 9 civilians, usually leaders in a scientific or technical field, meet periodically to act in an advisory capacity to the AEC for the purpose of enlarging the panel of talent and experience from which the Atomic Energy Commission can draw on in performing its varied and complete duty. Within the Department of Defense, the Director of Defense, Research, and Engineering acts as principal advisor to the Secretary of Defense on scientific and technical matters and supervises all research and engineering activities of the DoD. To assist him in this function, he has 2 subordinate agencies: the Technical Advisory Panel on Atomic Energy, which is composed of leading civilian scientists in the field, and the Coordinating Committee on Atomic Energy, which is composed of military members of the 3 services. The Military Liaison Committee, reflecting the military requirements of the Department of Defense, consults and advises the AEC on all matters related to the military application of atomic energy, including the development, manufacture, use, and storage of atomic weapons. The chairman of the Military Liaison Committee also occupies the position of Assistant to the Secretary of Defense for Atomic Energy. In this latter capacity, he provides the Secretary of Defense and principal members of his staff advice and assistance on atomic energy aspects of the Department of Defense policies, plans, and programs. Under the AEC, the Division of Military Application directs the research, development, production, testing, and storage of atomic weapons, manages related AEC installations and communities, and assists in maintaining liaison between the Atomic Energy Commission and the Department of Defense. These groups and committees are the high-level planners and arbitrators who ensure that the 2 separate agencies, the AEC and Department of Defense, work in complete coordination. Functioning under the Division of Military Application, the Albuquerque Operations Office, located in Albuquerque, New Mexico, is responsible for the research, development, testing, production, and storage of atomic weapons, and is vested with the power to make purchases and to let contracts. Through its several field offices, it administers related engineering, construction, and community program, and supervises the work of the private concern who operates under contract various installations on and equipped by the AEC for weapon research and production. The Sandia Corporation, the Los Alamos Scientific Laboratory, and the Lawrence Radiation Laboratory are principal installations doing research and development work. The Sandia Corporation, concentrating on ballistic shapes, electronics, hardware, and handling equipment. Los Alamos, the proving and testing of the high explosive components and the use of active materials in the weapon. Research and the use of active material is also conducted at the Lawrence Radiation Laboratory at Livermore, California, and is administered by the San Francisco Operations Office. When a new weapon is being developed and accepted for production as a stockpile model, work begins at the production installation. For example, the Bendix Aviation Corporation operates the Kansas City plant and, through their subcontractors, produce ballistic cases, electronic equipment, and hardware for weapons. Mason and Hanger, Silas Mason Company, operate the Pantex plant in Amarillo, Texas, to produce high explosive components. And in Rocky Flats, Colorado, the nuclear capsule components produced by the AEC's active material production plants are checked and assembled under a contract with the Dow Chemical Company. With the production of the components and the necessary phases of assembly, the weapon is stored in a stockpile ready for the time when it will be needed. Concurrently, within the Department of Defense, the Army, Navy, and Air Force have been preparing for their participation in the atomic weapons program through their individual organizations and the Defense Atomic Support Agency. All 3 services participate directly in the atomic program. The Ordnance Corps performs development and production functions for the Army and is currently responsible for such projects as non-nuclear components of Army atomic artillery projectiles and fuses for atomic warheads and Army missiles. The details of design and production are accomplished by Picatinny Arsenal. The Bureau of Ordnance, now called Bureau of Weapons, performs similar functions for the Navy. The supporting agencies of the Bureau of Weapons are the Applied Physics Laboratory, Naval Ordnance Laboratory, and the Naval Ordnance Test Station. The Atomic Technical Center for the Air Force is the Air Force Special Weapons Center at Kirtland Air Force Base under the Air Research and Development Command. The mission of the Special Weapons Center includes the responsibility for ensuring weapon compatibility to delivery vehicles and providing drop test assistance to the Atomic Energy Commission. Also, located at Kirtland Air Force Base, the Naval Air Special Weapons Facility performs the same two functions for the Navy. The Defense Atomic Support Agency has its headquarters in Washington and the Field Command located at Sandia Base, Albuquerque, New Mexico. The Chief, DESA, reports to the Secretary of Defense through the Joint Chiefs of Staff. In fulfilling its mission, DESA assists the Office of the Secretary of Defense and the Joint Chiefs of Staff, the military departments and services, and the unified and specified commands by providing technical, logistic, and training advice and services in the field of atomic weapons. It also supervises Department of Defense atomic weapons test activities. In providing technical services, the DESA provides up-to-date technical information on all weapons and test and handling equipment. Chief DESA is charged with the overall surveillance of the stockpile and is required to advise the Secretary of Defense as to the technical status of the stockpile. One of the primary vehicles for accomplishing this function is through the conduct of technical inspections. Still in the area of technical services, the DESA has considerable responsibility in the field of weapons effects and tests. After obtaining the requirements for information on atomic weapons effects desired, the DESA, in coordination with the services and agencies concerned, prepares an integrated full-scale weapons effects test program. Preliminary plans for the military phases of such tests are then prepared, and recommendations are made to the JCS as to the composition and command or control of task forces to conduct the tests, or to support the AEC in conducting the DoD portions of tests. At the conclusion of the tests, DESA prepares reports and analyses of the results and provides within the DoD a central agency for the collection and dissemination of technical information as to the effects, characteristics, reliability, safety, and vulnerability of atomic weapons. In the field of research and development, DESA provides primary DoD liaison and guidance to the AEC in those matters not appropriate for the MLC, conducts feasibility studies, prepares and submits the service-desired military characteristics for AEC-developed weapons, reviews AEC designs to ensure compliance with these military characteristics, and participates in the coordination of the development effort on atomic weapons approved for development. As for logistical services, DESA is responsible for consolidating the requirements for and effecting procurement of AEC-produced training weapons, operational suitability test weapons, test and handling equipment, associated repair parts, and other AEC-produced material. Arranging with the AEC and the services for the orderly dispersal and distribution of atomic weapons and associated repair parts. Informing commanders and the services of the estimated availability of atomic weapons to fill allocations and of technical limitations affecting the operational use of atomic weapons. Operating those stockpile sites used primarily to store and maintain the JCS reserve. Providing centralized coordination among the services and with the AEC in planning and scheduling modifications, modernization, and quality assurance programs to ensure minimum loss of weapon availability. Furnishing guidance on environment and construction standards for the storage and maintenance of atomic weapons worldwide to ensure optimum security and safety consistent with operational demands. In connection with its training mission, DESA conducts orientation courses for key civilians and military officers in the military application of atomic energy. It trains future atomic staff officers in the characteristics and effects of atomic weapons and in the technical considerations essential to their successful employment against an enemy target. It conducts specialized training courses for personnel from the services in the assembly, handling, storage, and maintenance of atomic weapons. In summary, it can be said that by accumulating and disseminating specialized technical knowledge, assisting in the basic and detailed training of personnel, and by coordinating and providing for many of the development and logistic requirements, the Defense Atomic Support Agency fulfills its mission to the military services and fits in its place in the complex national effort. Thus prepared, when an atomic weapon is produced and ready, either for stockpile or for use against an enemy, we will be in readiness for any assignment, whatever or whenever it may be. A nuclear explosion is the instantaneous release of a tremendous amount of nuclear energy. A nuclear weapon is the instrument which brings about the release of this energy. Nuclear energy comes from two processes that alter the nuclei of atoms. One is fission, and the other is fusion. First, let us consider the principles of nuclear fission. When the nucleus of an atom of a fissionable element, such as uranium-235 or plutonium-239, is struck by a neutron, the atom splits, or fissions, into two or more parts. The combined weight, or more correctly, the mass of these fission fragments, is less than that of the original atom. The lost mass has been converted into and released as energy. During and as a part of the fission process, another reaction has also occurred. 2 or 3 neutrons have been released and may strike the nuclei of other fissionable atoms, and thus continue the fissioning process. Essentially, it is a continuation of this action that makes a fission reaction possible. Because stray neutrons are always present, there are limits to the amount of fissionable material that can be assembled without producing a premature reaction. If the amount or shape of the active material is such as to permit the neutrons given off by spontaneous fission to escape after only a few fissions, the nuclear reaction is not self-sustaining, and the condition of the mass is said to be subcritical. If the configuration and amount of active material is such that one neutron from each fission does not escape and goes on to fission a new atom, a continuous self-sustaining reaction known as a chain reaction is created, and the mass is said to be critical. The sun is constantly creating and releasing energy created through a fusion process. Fusion is the second process through which energy is liberated from the nuclei of atoms. The process of fusion is the reverse of fission. In fission, a nucleus of an atom of high atomic weight is broken up to form other elements. But in fusion, the nuclei of two lighter elements are combined to make a heavier element and to release a great amount of energy. Fusion in nuclear weapons utilizes two of the isotopes of hydrogen to release energy. They are deuterium and tritium. Fusion will occur when the nuclei of the two atoms are given enough energy so that they can penetrate the repulsive force surrounding the nuclei. When the nuclei of deuterium and tritium undergo fusion, a helium particle will be created and a high-energy neutron emitted. A total energy of 17 million electron volts is liberated in the process. In order to produce a fusion reaction, the conditions of high temperature and high pressures found in the interior of the sun must be duplicated.
The Mark III, more familiarly known as the Fat Man, was our first implosion-type atomic weapon. Its prototype was first tested at Alamogordo, New Mexico in 1945. And later, a Mark III was used operationally against the Japanese city of Nagasaki. An improvement of the Mark III, the Mark IV, developed after World War II, was our first atomic weapon to be produced on an assembly line basis and to be stockpiled in large numbers. To give better ballistic accuracy, the shape of the case was changed. Provisions were also made so that the nuclear core of active material could be inserted without complete disassembly of the weapon by the use of a special detachable device. This gave us the capability of in-flight insertion of the active material. The firing system, commonly referred to as the X unit, and the fusing system were also improved and mounted on a cartridge to facilitate checking and testing. The Mark VI looks almost identical to the Mark IV, from which it was developed. But inside the 61 by 128-inch aluminum case, many changes have been made. Below the safing plugs, an easy-to-remove nose plate permits access to the horn-type radar antenna and allows for simpler and quicker in-flight insertion. Redesign of the entrance to the pit, addition of a detonator holding trap door, and coring of the high explosive makes it possible to slide the outer and inner cores of HE into a rotatable holder and permits manual IFI to be accomplished in a minimum of time. A single lug at the top of the ballistic case is used to suspend this 8,500-pound weapon from the bomb bay of the delivery aircraft. And extending through the skin are the arming wires that operate the pull-out switches upon release. This easy-to-remove cartridge is the electrical and electronic heart of the weapon. Readily accessible are the batteries, the radars, and barometric switches of the fusing system. The gap tubes and detonator contacts of the X unit are on the face of the cartridge. And inside the weapon is the detonator distribution system, with its loading coils to equalize the electrical paths to the detonators. When the cartridge is inserted in the weapon, pressure contact provides the connection between firing system and the terminals of the detonation system. In contrast with the Mark VI, which requires manual insertion of the nuclear material, The Mark V has a built-in mechanism to perform the insertion of the capsule and the cord high explosive. Thus, by a switch on his in-flight control box, the bomb commander of the delivery aircraft can automatically perform a nuclear insertion or extraction at any time. After the cartridge has been checked and installed, the tail section is attached, completing the assembly of this internally carried weapon. The need for a tactical weapon led to the development of the Mark VII. The two-piece ballistic case that encloses the components of the weapon give it the required streamlining to be carried externally. The Mark XII weapon, also designed to be carried externally, is even lighter and smaller than the Mark VII. Our above-ground capabilities with the implosion-type weapon are numerous. The Mark IX artillery-fired atomic projectile is for use in the Army's 280-millimeter gun. Thus, from our little boy and fat man, as new ideas have developed, and as technical hurdles have been surmounted, our family of atomic weapons has grown and will continue to forge ahead to meet the needs of modern warfare.
When the Department of Defense requirements for new or improved atomic weapons have been met, the various manufacturers under contract to the Atomic Energy Commission establish production of weapons and component parts for delivery to the designated AEC and military storage sites. Their arrival at one of the storage areas is not, however, the end of responsibility for either the AEC or the armed forces, but rather a continuation of the coordinated teamwork and concerted effort that made the testing, development, and production of war reserve weapons possible. The stateside sites or physical facilities where the weapons are stored may be under the operational control of the Field Command of the Defense Atomic Support Agency, as in the case of our national stockpile sites, or in operational storage sites operated by the logistic agencies of the Air Force, Army, or the Navy, and commanded by these services. The services are also in command of smaller storage sites, which are located throughout the world. Each site within the zone of interior is manned by a one-service organization. It is considered that from an operational standpoint and for administrative purposes, a single service organization is more efficient. A large segment of the organization's manpower is assigned to the task of providing security for the area. Patrols must be maintained around and within the multi-fenced perimeter. The Atomic Weapons Organization's highly trained technicians are charged with the important mission of inspection, maintenance, assembly, test, and modernization of weapons stored at the sites. These men, who ensure that our atomic weapons are ready if and when needed, attend specialized training schools. All all of the services conduct training in phases of the atomic weapons program of particular interest to that service. Field Command, Defense Atomic Support Agency, Atomic Weapons Training Group at Sandia Base, Albuquerque, New Mexico, conducts individual training for enlisted and officer personnel for the Army, Navy, and Marine Corps, and for personnel assigned to Field Command. Unit training is also conducted for personnel of the Army and Marines. The courses of instruction conducted by Field Command, DESA, provides individually trained nuclear weapons technicians for the Army and Navy. Also, personnel are given additional training in the highly technical aspects of radar and test equipment operation and repair. Unit training is provided for Army Ordnance Special Weapons, General and Direct Support Units, and for Air and Ground Marine Corps Tactical Support Assembly Teams. Air Force personnel receive all phases of weapons training at Lowry Air Force Base, Denver, Colorado, similar to that received by the other services at Sandia. Whatever their ultimate assignment in support operations, it will be trained atomic weapons personnel like these that will conduct the final preparation of our atomic weapons for their delivery on target. With respect to the storage of our atomic weapons, we find that the older weapons may have to remain in stockpile for an indefinite time, in which case, to guard against deterioration and to ensure that each weapon meets DoD reliability criteria, it is given periodic storage monitoring checks, ranging from limited inspections, where only certain components of the weapon are tested, up through a quality inspection of the completely assembled weapon. Commencing in 1956, a technique of packaging certain nuclear components at the time of manufacture was developed. These components require only limited inspection and testing prior to their use, and may be stored in operational configurations ready for immediate dispersal. Depending on the urgency of a combat situation, various weapon configurations are available. If time is an important factor, a weapon that has been in a ready storage condition may be selected for use. At a later phase of a war, an older weapon, which is in controlled retirement, may be selected. In such a case, the components of the weapon are checked for dependability by the atomic weapons personnel within the stockpile site before it is turned over to the using service. When operational experience or research bring about improvements in stockpile weapons, costly and time-consuming return of weapons to the factory is often avoided by in-the-field modernization and modification changes performed by these specialists. A major portion of inspection, maintenance, and modernization responsibility falls upon the shoulders of these atomic weapons personnel, who, whether at a storage area or assigned to an operational atomic weapons unit, are entrusted with the mission of preparing our atomic weapons for ultimate combat use. Thus far, we have discussed the phases of operations which can be referred to as the mine-to-stockpile sequence. We will proceed from this point with the stockpile-to-target sequence. Although air transportation is normally used, a weapon may make its trip to the forward staging area by various means, depending upon the particular priority and need of the service that is to ultimately use it. Dealing with the services individually, let us look at the Air Force first. A weapon to be delivered by the Air Force, depending on the physical facilities available, is loaded directly aboard the strike aircraft. A final inspection team can make the desired fuse settings and quickly run a functional test on the other components. Perform a post-loading check to see that all connections are made correctly and the weapon is ready for its mission. Where our smaller and lighter weapons are to be employed and the tactical or air defense situation demands, the weapon selected for use may be assembled at the stockpile site and the final and post-loading checks completed in the forward area by the personnel of an atomic weapons unit. Thus, by following an established plan, and with the use of an intercontinental bomber or missile as a delivery vehicle, we have, in the matter of hours or minutes, the capability of delivering an atomic weapon on target any place in the world. In addition to the aerial delivery punch of the Air Force, the United States Navy's formidable aircraft carriers today have the capability of launching atomic strikes. These highly mobile airfields receive their weapons in an assembled condition from strategically located storage areas. Once aboard ship, the weapons become the responsibility of the Weapons Division, which has the capability of storing, inspecting, assembling, and the final testing of weapons prior to their loading on strike aircraft. These units, whether they be Navy or Marine Corps, who may support both shipboard or shore-based Marine squadrons, keep their personnel in top efficiency by continual training and proficiency checks. In addition to its carrier-based delivery capability against land, air, sea, and undersea targets, the Navy also has a submarine and surface-launched guided missile capability. With respect to the Army, and to complete the overall picture of Department of Defense capabilities, Army Ordnance Atomic Weapons General and Direct Support Units have been provided to ensure efficient support in the stockpile-to-target sequence for atomic artillery shells, guided missiles, ballistic rockets, and atomic demolition munitions. The supply of Army-fired atomic weapons from the ZI to the using units is a function of specially trained ordnance units. The ordnance units may issue atomic weapons and nuclear components to artillery units at designated ammunition supply points. These units may be depots for storage of relatively large numbers of weapons for an entire theater, or they may be support units maintaining ammunition supply points in support of field armies and corps, or they may be small teams for limited or special applications. The nuclear components, projectiles, and warheads may also be with the firing units, such as Nike Hercules air defense batteries in the ZI and abroad, or various other artillery missile and rocket batteries. In these cases, ordnance maintenance teams will provide support. To sum up briefly, it might be said that the Defense Atomic Support Agency and the services train the skilled technicians who then join service or DESA organizations to prepare our atomic weapons from stockpile through the various and sometimes complex operations of making them completely ready for the day when presidential decree may send them against an enemy by Army and Marine artillery units, aircraft carrier strike, other Navy ships, by tactical aircraft, intercontinental bomber, and by guided missiles. This is an airburst of a typical nuclear weapon, exploded at a height of about 2,000 feet. The first observed effect is a brilliant flash of bluish-white light that overwhelms the vision of even distant observers. The ball of fire, an incandescent sphere of glowing gases whose internal temperature is measured in thousands of degrees, starts to climb into the sky. This particular fireball, a fraction of a second old, has an energy equivalent to 20,000 tons of conventional explosive. Its internal pressure is measured in thousands of pounds per square inch. As the luminous fireball grows to its eventual 1,000-foot diameter, gamma rays and neutrons are released to produce their lethal effect. Thermal or heat radiation ignites inflammable materials and inflicts personnel burns at relatively long ranges. The blast wave separates from the fireball and, traveling faster than sound, moves outward to batter the target area. This pulverizing shock wave forms a dust pedestal which seems to follow the rising cloud, developing into the characteristic mushroom shape of a low-altitude burst. Losing brilliance rapidly, the fireball is colored an orange-brown by the release of oxides of nitrogen from the surrounding air. Turbulent and still glowing, it shoots upward with an initial velocity of more than 100 miles per hour. As incandescence disappears, condensing water vapor begins to whiten the cloud. At still greater heights, ice crystals form and flow over the edges of the cloud to form a pure white color. Under certain atmospheric conditions, an ice cap may form above the cloud. Eventually, this cloud, with a diameter of about 3 miles, may reach an altitude of 50,000 feet. Then, slowly, it drifts away, mingling and blending with the clouds of the air until it can no longer be identified by the human eye. The destruction caused by a relatively low-yield weapon can result in many square miles of ruins and account for thousands of human casualties. But how did it all come about? What caused this destruction? What can we do to increase the destructive effect? Or conversely, how can we protect ourselves from it? Generally speaking, the main damaging effects of a nuclear weapon detonated within the atmosphere are blast, heat, and nuclear radiation. To add to our knowledge of the blast effects of a nuclear detonation on structures of known strength, an extensive test program has been carried out. Here, remotely controlled cameras record the impact of an atomic blast. Such a shock wave has a very long duration compared to that of conventional explosives. An atomic shock wave can envelop a structure and completely destroy it by pressure and dynamic wind effects. The damaging effects of the shock wave are maximized by a phenomenon called the Mach stem. This is a reinforcement of the blast wave by a reflected wave from the ground. This effect provides the basis for selecting an optimum height of burst associated with a particular yield to produce maximum destruction. With a higher yield of thermonuclear weapons, the distance at which destructive overpressure levels can extend and the duration time of the overpressure are increased to greatly extend the area of damage. In our tests, the Mach stem has been used against every type of structure: masonry, steel frame buildings, reinforced frame buildings, and wood frame construction. The side-on pressure, which hits a large building, can build up several times the pressure level occurring in the open. This is caused by the air piling up against the building. A secondary but very important aspect of blast effects on buildings and structures is the number of exposed and unprotected persons who will be killed or injured by the flying debris produced by the passage of the blast wave. This blast wave has a double destructive effect in that it is lethal to not only city structures, but also to a city's people. An interesting phenomenon in connection with the blast wave is called the precursor. It forms as a result of the heating of a surface layer of air by the thermal radiation. Light, although not a primary casualty producer, can cause temporary flash blindness to unshielded eyes. In addition, anyone looking directly at a nuclear explosion may suffer permanent eye damage even at very large ranges. Readily visible, day or night, the intense flash of white light is an easy identifying mark of the nuclear burst. No other type of explosion can equal it. Thermal radiation starts fires and causes serious burns on unprotected or lightly protected skin at long ranges. The combination of fire kindling and casualty-producing capabilities makes thermal radiation the most damaging single weapon effect against urban targets. As seen in these remote camera views, ignition of easily flammable fuels is almost instantaneous. Skin burns occur with similar speed. In most cases, evasive action from the brief flash of heat cannot be accomplished. However, anything that casts a shadow will afford some protection from this flash of heat. Ordinary clothing, as light-colored and loose-fitting as possible, offers excellent protection at distances greater than 1 mile. With an inflammable target, primary fires join with secondary fires caused by ruptured gas lines, electrical short circuits, and the like, to form a conflagration which may multiply the initial damage many times. In wooded areas, there is a possibility of starting forest fires, which might have a great effect on tactical situations. In an airburst, radiation is not the most serious consideration. Here, the largest percentage of the radiation is carried off by the nuclear cloud and dispersed throughout the upper air, presenting no problem to troops on the ground. The initial nuclear radiation is half over 1 second after detonation, and all over in from 10 seconds to 1 minute after the appearance of the white light. Penetration of initial gamma radiation is reduced by dense materials, 1 1/2 inches of steel, 6 inches of concrete, or 7 1/2 inches of ordinary dirt will cut gamma radiation by 50%. Take cover is the best philosophy for protection against nuclear radiation as well as from blast and heat. Even in this nuclear age, the foxhole is still the soldier's best friend. Although the airburst weapons comprise the largest part of our stockpiles, underwater, underground, and surface burst weapons also play an important part in military planning. As a part of the test series, underwater bursts were conducted against an array of target ships. Since the fireball is beneath the surface and the thermal radiation is absorbed by the water, there is no surface thermal effect. When the explosion bubble vents through the surface, an outward traveling shock wave is formed in the air. However, there is no augmentation of pressure by the Mach stem as in the case of an airburst. Significant from a military standpoint, however, is the tremendous column of water thrown up by the detonation. This water traps the fission fragments and is irradiated by the neutron flux. When the column rains out in the target area, it contaminates the target. The violent underwater shock makes a nuclear weapon capable of underwater detonation extremely effective against ships and submerged submarines. In the case of surface vessels, the surface water wave may also be destructive. In some aspects, the effects of an underground detonation are similar to an underwater burst. As in the case of an underwater burst, there are no direct thermal or nuclear radiation effects on surface targets. The air blast is somewhat lower than from a comparable surface or low air burst weapon, while underground shock is maximized. Most of the radioactive fission fragments are trapped in the dirt. Thrown up by the explosion, radioactive particles fall out on the target area, creating dangerous surface contamination. As in the case of the underwater detonation, this residual radiation will tend to restrict occupation of the area for a considerable length of time. A weapon with a yield around 20 kilotons, burst in dry soil 50 feet below the surface, will produce a crater approximately 650 feet in diameter and 140 feet deep. This cratering action, plus residual radiation, effectively denies the area to personnel, making an underground detonation effective against specific targets, including underground structures. The surface burst has some characteristics of both underground and air bursts. In a ground level burst, the thermal effect may be degraded due to absorption by the ground and the dust skirt. Blast overpressure, however, is much greater than with the underground burst. Residual radiation, being so much greater than the militarily insignificant amounts left after an air burst, contaminate large areas and have a definite effect upon tactical situations. The crater made by a surface burst is sizable, although its dimensions are much less than those from an underground detonation of comparable yield. All types of nuclear bursts must be evaluated, since each type has specific areas of greatest effectiveness. Residual radiation to contaminate areas. Blast to destroy structures. Thermal and nuclear radiation to kill personnel. A nuclear weapon represents potentials outside the concepts of conventional weapons. But this is not an ultimate weapon, nor one calling for unreasoning fear. It is merely another arm, another addition to our national arsenal. With prompt action, based on a thorough understanding of nuclear effects, our chance for survival in a nuclear war can be greatly increased. The story of nuclear weapons cannot terminate with an explanation of fission weapons, their principles of operation, and effects. As has always been the case, man's development of the tools of war is a fluid, ever-changing pattern. For a few short years, fission bombs were the ace in the hole. But science continually explores the atom's secrets, and theories soon become facts. Fission weapons were not replaced, not obsolete. Rather, they were augmented by the new power, the thermonuclear weapon. This is the story of the historical development of such weapons now being added to our national stockpile. The United States has, through use of the Pacific Proving Grounds and Nevada Test Site, culminated years of laboratory work and research and taken great strides forward in the field of nuclear weapons. Until late in 1949, it seemed that major emphasis pointed toward further development of stockpile fission weapons. This was correct. However, it was but a part of the story. Scientists knew the blueprint for mass and energy. They knew how to cause the splitting or fission of heavy atoms to produce an explosive chain reaction in the case of oralloy and plutonium. When fission occurs, the total mass of the two fragments is less than that of the original mass. That difference is energy. Fusion, as the term implies, is a fusing together of two atoms into a single nuclear unit, the direct opposite of fission. But still, for light atoms, the new mass is less than the combined masses of the original atoms. Is a man-made thermonuclear or fusion reaction possible? This was the task facing our scientists. They knew the reactions on the sun were of this kind. Very probably, it was the fusion of hydrogen taking place over millions of years. But an instantaneous fusion reaction occurring in a few millionths of a second was needed. To obtain this, heat was needed, for heat is essential to a thermonuclear reaction. Temperatures the order of millions of degrees centigrade, many times the surface temperature of the sun, were needed. There was only one source of such temperature, a fission bomb. So, not until the fission weapon was perfected did science have the match, so to speak, to ignite the main reaction, fusion. Science was not given time to patiently experiment and develop the hydrogen bomb. The world situation dictated the President's announcement in January of 1950 that this country must develop a thermonuclear weapon as soon as possible. The hydrogen bomb was to become a reality instead of a subject for theoreticians. Common hydrogen has the simplest nucleus known. It has one proton. But hydrogen exists in two other isotopic forms, deuterium, which has a neutron in addition to the proton, and tritium, which has two neutrons and one proton. The first step was to determine if a suitable material, a good bomb fuel, was available. Laboratory evidence proved that ordinary hydrogen, the common element used so frequently and inexpensively, was definitely not suitable as a thermonuclear fuel. But it was believed rare forms of hydrogen would work, namely the two isotopes, deuterium and tritium. Another problem was determination of the proper state in which the fuel must be kept. There are three possibilities: gaseous, as hydrogen normally exists; solid, wherein it is bonded with another element, possibly lithium; or liquid, requiring very low temperature. Deuterium is obtained by relatively simple chemical means, while tritium is pile-produced, a complex and costly process. Deuterium alone is far and away the most practical fuel. However, there was considerable question regarding its reaction time, its ability to ignite during the fraction of a microsecond that the required degree of heat is available. There was also question whether tritium atoms would fuse with each other. On the other hand, studies indicated a reasonable probability that tritium would fuse quite readily with deuterium. A mixture of the two, then, a DT mixture, stood a chance of successfully reacting. This was the direction taken leading to Operation Greenhouse in the spring of 1951. Here, the first thermonuclear experiment in recorded science was to occur. At Greenhouse, with a George shot, small, nearly equal amounts of deuterium and tritium were taken, brought down to a liquid state, and put in a refrigerated container close to a fission device. George was designed to determine if fission energy could fuse a deuterium-tritium mixture. This could be detected by measuring high-energy neutrons produced by fusion reactions. Of tremendous significance was the fact that high-energy neutrons, peculiar to fusion reactions, were detected in quantities higher than anticipated. This was definite proof that fission weapons were suitable for providing the energies required for the fusing of deuterium and tritium. The end result was that a program dealing with wet weapons, that is, those weapons carrying their fuel in a liquid state, was adopted, leading to Operation Ivy and Mike in the fall of 1952. Mike, the great physics experiment. 21 feet high, 80 inches in diameter, and weighing some 80 tons. Mike was not a weapon. It was far removed from anything resembling one. Mike was purely and simply a laboratory-type experiment, a tremendous gadget with its fuel, pure deuterium, maintained in a liquid state. It stood there, surrounded by its cryogenics equipment, for to maintain the hydrogen fuel in a liquid state is a tremendous undertaking in itself. The problems connected with very low temperature operation had been met on greenhouse. Those problems increased by an order of magnitude on Ivy. The heavy hydrogen fuel for wet weapons must be kept in a liquid state, so a temperature of less than minus 417 degrees Fahrenheit must be maintained, just 42 degrees above absolute zero. Cryogenics became a major factor in development of deliverable thermonuclear weapons, and the services went ahead on a full-scale basis with the wet weapon program. Within its Pacific Island laboratory, Mike stood ready for a most significant moment in weapons development. This was the first full-scale test of a hydrogen device. If the reaction goes, the thermonuclear era has arrived. The physics experiment ended, and with it came the wealth of diagnostic data to be digested. Mike was successful, but it was still a device, testing a principle, not a deliverable weapon of war. So, as of November 1st, 1952, we had the principle, but lacked the real weapon. During the months after the Mike detonation, preparations for a new series of tests to solve the problem of a deliverable megaton weapon went on at an accelerated pace. All this leading to Operation Castle at the Pacific Proving Ground in the months of March, April, and May, 1954. Certain tests carried out at the Nevada test site materially increased the stockpile of weapon data. Tremendous amounts of time and money were saved by conducting tests here rather than the Pacific Proving Ground. Operations Tumbler Snapper and Upshot Knothole, held during 1952 and 1953 respectively, provided information on case construction and included studies of other associated nuclear processes. Contributions of the Nevada test site were vital and significant in the thermonuclear weapon field. The emergency capability weapons that were being hurriedly built for the stockpile were proof tested at Bikini and Enewetak atolls in the early months of 1954 during Operation Castle. In addition, valuable information was gained which was to lead to a new family of thermonuclear weapons of improved design and quality. Castle had 4 objectives. 1, assurances that emergency capability weapons did, in fact, fulfill the requirements placed on them. 2, an evaluation of dry versus wet thermonuclear fuels. 3, reduction of size and weight in future weapons. 4. Obtain effects data on large-yield weapons. Castle was a 6-shot test, 5 at Bikini and the other at Eniwetok. From this operation, we learned the answers to questions on the behavior of thermonuclear weapons and their fuel systems. We found that the intricate and cumbersome problems of cryogenics born with Mike Shot in 1952 could be canceled out and emphasis put on dry or solid fuels. Thus, in a period of 15 months, the wet program was obsolete. Castle was a success. The achievements from this one test are proof enough. The wet weapon program was dropped and all attention focused on dry fuel systems. Vital data on effects of high-yield weapons were obtained. Definite reductions in the amounts of costly, hard-to-get tritium and increased knowledge in the use of light element fuels necessary for weapon function was another Castle bonus. And by far, the most important item was the emergency capability program. Castle proof-tested vitally needed weapons, deliverable weapons for the services. Tangible, immediate benefits gained from Castle are the TX-17. Weight, 41,000 pounds. Length, 24 feet. Diameter, 5 feet. This is the largest weapon in the thermonuclear family. The TX-24, its sister weapon, is identical externally and differs only in nuclear components. The TX-21, weight about 18,000 pounds. It measures 150 inches in length and 56 inches in diameter. The TX-21 is essentially a scaled-down TX-24. Its sister weapon, the TX-36, is identical externally. The TX-15, a small, relatively low-yield weapon of 8,000 pounds. The TX-15 measures 11 feet 6 inches in length and less than 3 feet in diameter. Its uses will be varied, and it can be carried by a wide range of aircraft types. TX-14 was fabricated in small quantities to augment the stockpile. It was very similar to the TX-17, but shorter and lighter, measuring 19 feet in length, 5 feet in diameter, and weighed just under 30,000 pounds. While smaller and lighter than the 17, its cost in active materials was considered to be too high to constitute a practical weapon, and hence the 14 has been retired from stockpile. These weapons fulfilled most of the military requirements for 3 of the 4 general classes of thermonuclear weapons as then laid down by the JCS. Class A, TX-17 and TX-24. Class B, TX-21 and TX-36. Class C, TX-15. The TX-15 exceeds the desired weight limitations by approximately 1,000 pounds. Class D, a weapon in the design stage weighing not more than 3,000 pounds, a requirement for future development of a new family of thermonuclear weapons to ultimately replace those now in stockpile, has been stated by the Joint Chiefs of Staff. This requirement redesignates the weapons classes. However, there is much more to a thermonuclear weapon than its size and weight. It is inside where the big payoff comes. There are 2 main units making up any weapon of this type. The first of these is the primary. The other main unit is the secondary or thermonuclear portion. When the primary or trigger bomb is fired, energy is transferred to the secondary. If certain of the light elements are raised to sufficiently high temperatures, temperatures available only in the detonations of an atomic bomb, these elements may be caused to fuse together and be transmuted to heavier elements. This fusion process is accompanied by the release of tremendous amounts of free energy. This has been a brief resume of the development and operations of thermonuclear weapons. But what of the effects, the aftermath of an explosion in the megaton range? George shot. 0 point was the island of Eberiru. George left a crater 1,000 feet across and 10 feet deep. Mike. 0 was the island of Ilujilab. The crater was 1 mile in diameter and sloped down to a maximum of 175 feet. An entire island was vaporized and sections of islands on either side were chopped off. This is the island of Enenman, Bikini Atoll, 15 miles from 0 point, the first shot of Operation Castle. This too is Enenman, 15 miles from 0. Castle provided the military with the opportunity to record and study the effects of multi-megaton weapons and aided them in the revision of previous military concepts dealing with low-yield capabilities. For example, initial gamma radiation at ranges of concern was only about 1/10 of the predicted intensity. It was found that initial gamma from high-yield weapons becomes militarily unimportant in those ranges where blast and thermal continue to cause almost 100% casualties outside of heavy bunkers. Measurements of neutron spectrum and flux were made, but while the neutron flux was heavy, it attenuated so rapidly with distance that no military value was attached. The significance of fallout from high-yield surface detonations becomes increasingly important from the military viewpoint. Fallout begins with the millions of tons of earth vaporized or thrown out by the explosion. It traps radioactive fission products while being drawn to great heights within the cloud. The main fallout pattern appears to have been dominated by winds between 20,000 and at least 70,000 feet, with some influence exerted on the pattern by winds outside this band. A shower of radioactive particles drop from the cloud as it is carried along by these winds at rates determined by individual particle size, so that many hours are required before the pattern is complete. Although fallout was studied in the classic way, the high yield plus a wind factor caused contamination of distant populated atolls, providing a completely new source of study on these effects and showing graphically the tremendous area of contamination from a high-yield surface burst. 229 natives and 28 American service personnel received doses ranging from 12 to 200 Roentgens. Shortly after the shot, they were evacuated to Kwajalein for treatment and observation. None of the doses appeared to reach levels of immediate combat significance, nor did the people suffer severe effects. Also of great significance was determination of what appears to be the main fallout pattern. This pattern is difficult to predict and is subject to many variables. It settles to Earth in a design which can reasonably be called a long leaf shape. Analysis of data indicates that for a surface detonation of a high-yield weapon, an area of approximately 7,000 statute square miles can be covered by contamination at levels that might be lethal to some 50% of exposed humans. Some approximate areas such a fallout pattern could encompass within the United States would be an area running from Milwaukee east beyond Detroit, from Denver east to Lincoln, Nebraska, from Los Angeles east to Flagstaff, Arizona. In summary, the fallout from high-yield surface bursts, such as those during Castle, presents many problems related to civil defense. However, passive defense can drastically reduce casualties. The shelter of a frame dwelling will cut the dose rate to 1/2 of the outside rate, and a position in the basement would reduce it to 1/10. Attenuations in excess of 1,000 can be gained in basements or middle stories of multi-story buildings, or in simple shelters with at least 3 feet of earth overhead. The seeking of optimum shelter for a minimum of 2 to 4 days appears to offer the best chance for survival. In areas some distance away and downwind from the point of detonation, a period of 5 to 10 hours may be available in which to seek shelter before fallout begins. The first studies on blast from megaton weapons were made on IV Mike. Castle provided a check on these figures and added some of its own. However, the real military importance of high-yield blast effects lies not in their type or quality, but in their enormous range compared to kiloton weapons. A 100 kiloton weapon at optimum height will cause severe damage over an area of 5 square miles and moderate damage over 12 square miles. Contrast this, 5 and 12, with 80 square miles of severe damage and 240 square miles of moderate damage from a 15 megaton surface burst like Castle Shot 1. 240 square miles, more than 20 Hiroshimas in a group, more than 10 Manhattans, in which blast compounded with fire may bring almost total destruction. The big bonus from multi-megaton weapons is the longer positive phase, producing blast damage far beyond that of kiloton weapons. Many other projects made up the effect studies on Castle. For example, drone Liberty ships were utilized to aid in perfecting washdown techniques for vessels caught in fallout areas. No thermal military effects tests were scheduled on Castle, but measurements were made of the thermal spectrum, power versus time, and total energy. Power versus time graphs show that the main thermal pulse of a low-yield weapon arrives and is essentially completed inside of a couple of seconds. From a high-yield weapon, it takes some 3 seconds to reach the peak of the main pulse, which has a comparatively long duration. Therefore, quick dodging into even light cover would allow target personnel to escape most of the thermal effects. The slower delivery time also requires a scaling up of low-yield thermal damage criteria. Equivalent damage from a 1 megaton bomb requires twice as many calories as would be required for a low-yield weapon. The needed increase approaches 350% for 15 megatons and probably still more for higher yields. But even with these handicaps, the thermal destructive range of megaton weapons is huge. Against exposed troops wearing 4-layer winter uniforms, an optimum burst height with a 100 kiloton bomb can produce 50% casualties out to nearly 2 miles, involving an area of 10 square miles. A 15 megaton burst will, even after tripling the calorie requirement, produce these 50% casualties out to the edges of a 75 square mile area. Lighter clothes will greatly extend the area. Extending the comparisons, it can be seen that the 100 kiloton weapon will probably cause heavy primary or secondary fire damage in average cities over about the same 10 square miles that fitted the 50% casualty probability. A great many small trash and litter fires would be initiated over some 25 square miles. Using the 15 megaton bursts, it is possible to get very heavy fire damage over 75 square miles, and the sporadic small fire area may become in excess of 200 square miles. No estimate can be made as to how many of these fires would survive the blast winds, but based on Hiroshima and Nagasaki plus test experience, destruction could be extensive. Castle also provided more data on the problems of delivering multi-megaton weapons by aircraft and the blast and thermal effects on such planes. A B-36 at 57,000 feet slant range and a B-47 at 62,000 feet slant range were used, the B-47 providing a means of extrapolation to the B-52. The B-47 participated on 5 of the 6 Castle shots and was positioned where it should receive the theoretical maximum allowable temperature rise, 370 degrees in the aileron skin. The B-36 flight patterns placed it tail-on toward all but the last shot, for which it was flown head-on for both the thermal and blast phases. As a matter of record, no prompt gamma or fallout problems were encountered by either test aircraft. Thermal damage was in all cases minor, involving only some patches of blistered paint at various points. Because of the B-47's high escape speed, the highest overpressure recorded was about 1/3 of a pound, and the only blast damage was a split rubber coupling on the in-flight refueling manifold. Visual thermal damage consisted of some permanent skin buckling on the elevators, plus burned paint on other areas. Sponge rubber burned around the lower aft blisters, which also cracked, either from thermal or shock, or both. Blast damage included characteristic dishing of wings, under nacelles, bomb bay doors, lower turret and landing gear doors, spotty rivet failure, and severe crushing of the radome. In totaling up the preliminary data from these studies, it was found that both the B-36 and the B-47 can be used for the delivery of multi-megaton weapons up to castle size. However, this is not the only thermonuclear delivery capability. The Department of Defense and Armed Forces Special Weapons Project maintain an ever-expanding plan for the design and proof test of new vehicles for delivery of thermonuclear weapons to fill the needs of the armed forces. It is possible to touch on only a few of the many programs and projects executed on an operation such as Castle. The big point is, they were followed through to conclusion. Facts, data, information were obtained, correlated, and disseminated. The nation's stockpile, the thermonuclear stockpile, became a reality. This is a thermonuclear weapon detonated on Bikini Atoll, as it was witnessed on Eniwetok Atoll, 200 miles away.